In the late 1700s, chemists were beginning to realize the importance of making careful measurements, and in particular, keeping track of the mass of the materials used in their processes. Along the way, they discovered some laws about mass. Then, in 1803, John Dalton published what has come to be known as Dalton's atomic theory. He was trying to develop a theory that would explain the three mass laws that were known or being developed at the time. Remember that a law is a simple statement of consistent observations. A theory goes deeper in that it tries to explain the observations. Let's look closer at the laws and then at Dalton's theory. The first mass law that Dalton tried to explain was the law of definite proportions. This essentially states that if you have a compound, such as water, the hydrogen to oxygen mass ratio is always the same, regardless of where the sample comes from. The second law is the law of multiple proportions. There are two common compounds that contain hydrogen and oxygen, namely water and hydrogen peroxide. If you took samples of the two, each containing 1 gram of hydrogen, then the mass of oxygen in the hydrogen peroxide sample would be exactly twice the mass of oxygen in the water sample. Thus, a simple mass relationship exists between the two compounds. The third law is the law of conservation of mass. During a reaction, the total mass of reactants and products stays constant. Dalton was able to explain all of these by invoking the idea of atoms. We know today that exceptions to these laws abound, but in Dalton's day, these observations led him to develop his theory. Dalton's atomic theory has three parts. First, elements are composed of atoms which, for a given element, all have the same properties and mass. This helps explain the law of definite proportions. If all hydrogen atoms are the same and all oxygen atoms are the same, then all water molecules must be the same as well. We know today this is not completely true. There are isotopes of elements that have different masses. Thus, heavy water, which contains deuterium, a heavier isotope of hydrogen, is different from regular water. We'll look at isotopes later. Second, when elements form compounds, the atoms combine in small integer ratios. This helps explain the law of multiple proportions. If there are integer ratios of atoms, then the masses of the elements in different compounds should be related to each other in a simple way. While this is true for materials which exist as discrete molecules, we know today that many interesting solid materials have defects in their structure and have inexact atomic ratios. Third, during reactions, atoms don't change. They simply rearrange. This helps explain the law of conservation of mass. If all of the atoms present at the beginning of a reaction are still there at the end, then the mass should not change. It should be conserved during the process. We know today that in some processes, such as nuclear fusion reactions, mass is converted to energy and thus not conserved. However, even with all these exceptions, Dalton's theory still pertains to simple chemical processes that involve molecular substances, and thus gives us a basis for starting our exploration of chemistry. It's worth noting that the three parts of Dalton's atomic theory follow the outline of our course. We'll start with atoms, move on to compounds, and, after thinking about materials, end up with reactions. Dalton's theory deals with atoms, compounds, and reactions, so we can return to this theory throughout the course. While it took the better part of a century for Dalton's theory to be universally accepted, it finally became the standard for describing substances and their reactions. Despite the exceptions to the mass laws on which Dalton's theory was based, the fundamental idea of atoms and how they behave continues to provide the foundation for how we conceptualize chemistry today. Maybe the most important idea to come out of this theory is the idea that we need to think about what the individual atoms are doing. In quantifying materials and reactions, we need to keep track of how many atoms are involved. When we talk about a glass of H2O, we're not describing the masses of hydrogen and oxygen. Rather, we're saying that there are twice as many hydrogen atoms in the glass as there are oxygen atoms. Now, we might measure the mass or volume of a material, but it's the number of atoms and molecules that is most important.